Now, since we have learnt about definitions of work and got two different formulas based on the definition, it's time to check if we can apply these formulas or the right formula to solve a problem based on this concept. Let's read the question. A force F, this F is in bold letter meaning a vector quantity, and that's unit vector notation, writing in terms of I, J and K. 5i minus 2j minus 4k Newton. This I, J, K also are in vector quantities. They are called unit vectors and they are also in bold letters. Acts on a particle of mass 1.5 kg to change its position vector from I minus j plus 2k meter to 3j minus 3k meter. Find the work done by the force on the particle. So we have got two formulas learned recently, and let me write them and see which of them applies to do this problem. One definition was, of course, W is given by Fs cos theta. That was I called equation number 1. And here you can understand that work is a scalar quantity, its magnitude only has got. So it's given by magnitude of the force applied, magnitude of displacement into cosine of the angle between theta between F and S vectors. Another way of writing was, of course, in terms of scalar product. Work is the scalar or dot product of two vectors, F vector dot S vector. Now that is my equation number 2. So we shall see which of them we can apply here to do this problem. So the question says the force given was 5i minus 2j minus 4k Newton. Now this is called unit vector notation, where we express force in magnitude and direction. Both are expressed by this method. In terms of I, J and K, they are all unit vectors in the plus x, plus y and plus z directions respectively. This is a problem in 3 dimensions. You write the coefficient of I, J, K in the front with proper sign here, and while writing in printed books you can see this I, J, K as well as the force are written in bold letters, but in handwritten stuff you must be giving this arrow sign on top, or here you have been given caret symbol, C-A-R-E-T, caret. It's like a cap. That means they are unit vectors. So force is 5i minus 2j minus 4k Newton. Don't forget to write the unit outside this bracket. The mass of the particle given is 1.5 kg. We have to see where we can apply that. And position vector of the particle initially, that is R1. See, one symbol I use for initial value and usually two symbol, that is subscript, for final values. So initially the position vector was I minus j plus 2k meter. Once again we write the units outside. I minus j plus 2k meter. Finally it has gone to R2. This 2 is the final position, and that is 3j minus 3k. So all are unit vector notation. Now that's going to help us to find both R1, R2 and F in magnitude and direction if required. This is called the unit vector notation of any vector representation. So here, as we can see from the formulas, we can guess we require possibly this formula number 2, because work is given by the dot product of force and displacement vectors, and force as a vector is given by this formula here. So obviously the magnitude part is not given in the question. They have given straight away the force as a vector. So I might give my attention to this formula number 2. This is, we must now focus on. This is the formula. W is equal to F dot S. F already is known. This is given here. But what about displacement? That displacement is of course S, and we have to find what is this from this question. Okay, so we have only been given the position vectors initial and final, and let us recollect why we can apply vector algebra to get this displacement S here. So we construct a figure, a simple figure rather in 2 dimensions, because the problem was given in 3 dimensions, but that does not pose any problem to understand and recollect rather what we have learnt in vectors. So here we draw a simple 2-dimensional coordinate system, as you can see. And suppose a particle is moving in this xy plane in a curved path as given by this line that I am drawing. And obviously I mean that the motion is, the particle is moving like that. And initially the particle here is this point that I called P1. Later it comes somewhere here, that is the point P2, and correspondingly the position vectors of the particle initially was this, now, and finally the position vector has come here, that is origin to the point P in question. So let me name it. This is the x direction, that is the y direction. This is the origin of the 2-dimensional coordinate system, and as the particle travels from P1 to P2, its position vector has changed from R1 initially to R2 finally, that is this. And we can apply vector algebra to show that the displacement of the particle is simply given by this arrow P1, P2. So here if we apply in the triangle OP1, P2, you can see that by triangle law of vector addition, this OP1 plus P1, P2 vector, they together must be equal to the third side in reverse order, that is coming out to be OP2.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.